Welcome back to IPAC. This is Peter's fourth lecture out of 5. And go ahead, Peter.
Thanks. And now we're starting to get deep into the Lorentzian polynomials. And I guess it's some of the things are getting technical, but soon we'll get into applications which will not be too technical. But then we will get technical again when we will try to sketch a proof of this Hebron-Rota-Welsh conjecture. But first I'd like to do a recap. So we saw that so we looked at the M convex sets, and they are particularly nice when the rank is 2. We have some loops that are not sort of that are not in the support at all, and then we have the parallel classes, sort of as in matroid theory, and then we have these special elements that the set T, which were the ones where 2EI is in the M convex set, and then we concluded that we have a sort of a complete graph here, and by an edge, I just mean that between an edge between I and J, I just mean that EI plus EJ is in the set. So one feature of this is that if yep.
May I ask something? Yeah. So like there's no elements like 2EI plus EJ. Is it because it will be in rank 3?
Yeah.
And rank will be the same as the sum of the coordinates, right?
Exactly. Exactly. So the rank is the sum of the coordinates, which we know are the same for all elements in the M convex set.
Okay.
Exactly.
Thank you.
So what we can see now, so the supports of the quadratic Lorentzian, so quadratic Lorentzian were the same as quadratic stable. So these are stable polynomials, and we proved that stable polynomials have M convex support. So from this we can deduce that if we can, this we had this notion of regularity of the matrix, said that sort of the non-zero entries of the matrix forms a connected set. So we can go from one non-zero entry to another non-zero entry, going by a common coordinate. So from this we see, from this picture, it's evident if the derivatives are non-zero, this means that we have no loops. But then we can go from any vertex here to any other vertex in this graph, or we could go directly here, or we could go from here to there. So then it's sort of obvious from the support being M convex that the matrices, the Hessians, are regular, and this we'll use later. But we were trying to prove this theorem by her and myself, namely that if we have a homogeneous degree D polynomial with non-negative coefficients, then this polynomial is Lorentzian if and only if these two conditions hold. Namely, the first condition is a combinatorial one, saying that the support of F is M convex, which is usually easily checked. And the other one is this sort of having just one positive eigenvalue. But now we only have to check it for coordinate directions. So for all tuples I1 through ID-2, the Hessian of the derivative should have at most one positive eigenvalue. And we could prove that we could prove one direction, namely that if it's Lorentzian, then these two are satisfied. But we're left with proving the other direction. And we also said that if we could replace this, this condition L here is equivalent to being stable, which we saw before. So let us also recap what we meant by a C-Lorentzian polynomial. So this was two condition, a positivity condition, saying that when we take mixed derivatives in the cone, then we have positive coefficients. So we have positive mixed derivatives, and we have this Alexandrov-Frenkel inequality, which we can use to prove log concavity and ultra log concavity. And we also noted that we can replace this Alexandrov-Frenkel inequality with an equivalent condition that has to do with this one positive eigenvalue, namely that when we differentiate d minus 2 times with directions in the cone, then we should have exactly one positive eigenvalue of the Hessian. And then we gave a special name to the case when we're in the positive orthant, then we say that we simply say that this polynomial is Lorentzian. Okay.
Peter,
Yep.
in your AF replacement, what you call L, when checking the Hessian, does it suffice to go in the unit directions?
So this, if we differentiate d minus 2 times, then the Hessian is a constant matrix, right? So if we have a quadratic polynomial and we want to look at the Hessian is the di dj f. But since it's a quadratic, then it's just going to be constant. So it doesn't matter, you can't plug in any vector.
So the VIs can be replaced by EJs, DJs.
No, okay, sorry. That was your question.
Yeah.
For the case of Lorentzian, this is sort of the context of this content of this theorem, right?
Right.
So you might be, so June and I, we had a different notion of Lorentzian actually, but since we want to talk about C-Lorentzian polynomials, I actually have a different notion of Lorentzian polynomials. So that may be what sort of confuses you.
Mm-hmm.
But this is the definition that we will work with. But there are, for the positive orthant, there are many different definitions.
Mm-hmm. Thank you.
Okay. So we're left with proving the other direction, that these conditions M and P and M, well, M and L, I call them, right? That these conditions M and L implies that the polynomial is Lorentzian. And for this, we will use this Bochner method. And that this Bochner method says something of this sort, right? It says that it sort of makes us use induction, because we can, if all the derivatives, if the Hessians of all the derivatives have exactly one positive eigenvalue, and we have this positivity, and we have this regularity, which we will have for free, then actually F will have exactly one positive eigenvalue too. So we will use this. So we want to prove that. So we want to prove that this M and L implies Lorentzian. And this is by induction. So we let L prime be the class of polynomials, or the set of polynomials satisfying M and L. and L to be the Lorentzian polynomials. So we
We're
want to
talking about homogeneous, right?
yeah, homogeneous with non-negative coefficients. So now we want to prove that, well, we want to prove that if we prove that, well, L prime is a subset of L by induction over the degree. Okay. And we start with d equals 2. But then we have nothing to prove. If d is 2, then, well, if we go back here, well, this is, if d is 2, then we have no, then we don't have to do any derivatives of at all. So this only says that f has exactly, the Hessian of s, f has exactly one positive eigenvalue. And also for this, here we don't have to consider it. We only have to consider the empty sequence here. So only that f has at most one positive eigenvalue. So for d equals 2, this is trivial. Or trivial by definition. So then we assume d is greater or equal to 3. And what do? Well, we want to prove what is left to prove is that this positivity condition is for free, since we have non-negative coefficients. And if you take derivatives with in directional derivative with respect for vectors in the positive orthant, then we're going to have a positive real number in there. So we want to prove this that the Hessian has exactly one positive eigenvalue. So we want to prove that what do we want to prove? We want to prove that this has exactly one positive eigenvalue. If f is in this L prime. And we do this by induction. But we know that, so the Hessian of this is just going to be a constant matrix, right? A matrix with real entries. And one can see that this the Hessian of, but this is equal to, so this Hessian is equal to the Hessian of G, which we define to be instead dB1, dB2 up to dB d minus 3 instead. So we just so we have a cubic instead of f. Sorry, but evaluated at x, where x is bd minus 2. And this is easy to check, because the Hessian of this is going to be the Hessian of G is going to be so the entries are going to be linear forms. And if we take another derivative with respect to d minus 2, then it's the same as evaluating at that. So this is not hard to see. Oh, sorry. wrote this a little. Rewrite it. So the Hessian at x equals VD minus 2. Okay, so now we're sort of set up for this Bochner lemma. So we apply this Bochner method. So we want to check. So by induction now. Okay. Yes. So now yes. So now if we look at this, we want to check that the derivatives are now Lorentzian, right? To apply this, or they have we want to deduce that that the derivatives have Hessian with exactly one positive eigenvalue. And to do this, we write this as this is by definition but and by induction this DIF well by definition almost by definition DIF is in this L prime, so by induction DIF is in L, since it has 1 degree less. But now this taking derivatives, taking directional derivatives preserves the property of being Lorentzian. So so this so this dig being db1 through db d minus 3 DIF is also Lorentzian, since taking directional derivatives preserves the property of being Lorentzian. So since this is
Peter, sorry, are we sure G is now having support M convex?
so this I will this is the next step.
Okay.
So but now we know that this dig is Lorentzian, so it has the Hessian of dig has exactly 1 positive eigenvalue. And this is one of the conditions that should be hold to apply the Bochner method. And the other one is this regularity. So this is what I'm saying now. So this the Hessian of G at x in Well, then I claim that this is regular. And why? So since the support, well, the support of the Hessian, meaning the non-zero entries, is equal to the support of when we truncate d minus 2 times the support of f. And the support of f is m convex. And why is this? Well, we know that this taking derivatives with respect to the positive orthant, what it does to the support is just truncating the support. So we truncated it down d minus 2 times or 3 times. D minus 3 times here, but we do it one more by evaluating x equals this. So Bochner, so the conditions in Bochner holds. So Bochner implies that the Hessian of G at x has exactly one positive eigenvalue. And as we said, this is exactly what we wanted to prove because this is the Hessian of this, of what we, this is the Hessian, the matrix that we want to look at. The construction was that they agreed, these two Hessians. So this is what we want to prove. So we have this, so this Bochner method that I haven't proved, but I've put up a detailed proof of it if you're interested in it. Then this implied directly this other direction of this characterization that we now use. So this characterization has these 3 properties that we should remember now. That we should check that the support is M convex, and when we take derivatives with respect to the coordinate directions down to quadratic, then it should have at most one positive eigenvalue, or equivalently that these derivatives are stable. Okay. So now we go back to this. So what we now want to do is we want to see that actually this theorem characterizes M convex sets. So we've seen that the supports of the Lorentzian polynomials are indeed M convex, but we haven't seen that all M convex sets arise in this way. And this is what we want to do. And to do this, we want to look again at this, the case of rank 2. And we're familiar with this now. But if we now define this exponential generating polynomial of an M convex set, so we just we take all the vectors in the set and we take x to that, so and we divide by alpha factorial. So these are, of course, these are multivariate. So if we want to do this for a rank 2 set now, so if we divide by alpha factorial, so the only, since we now have rank 2, so the only ones that get, that get something in the denominators are the ones in T. So the ones in T, for them we get xi squared over 2. And for the ones, we get nothing for the loops. And for the parallel classes, we just get, and we get a monomial xi, xj for all I, j, and m, where of course. What have I written there? So this should be something else. So. Let me write it this way. Okay, this is certainly true, but it's not hard to see that this actually is equal to this sum of squares with signs. And why is that? Well, if we look, so if we're in T, then we'll get xi squared over 2 from one of these terms, right? And we will get no cancellations from these terms. So these are the parallel classes, these up here. And otherwise, if we're for the other squares in here, they will cancel by the squares in here. Okay, and we will get no, and we will get linear. Well, we'll get terms like this from. We will get no terms like this. These will cancel from here to there too. So we will only the only ones that survive are the ones. Are these ones and these ones. So this is not hard to check. So what does this imply? Well, it implies that the Hessian of this PM is negative semi-definite on this hyperplane where this is 0, right? Because if this is 0, we get something non-positive here, just by definition. And then we have this Cauchy interlacing and Silvestri law of inertia that says that then, but then the Hessian has at most one positive eigenvalue. But then if it has at most one positive eigenvalue, well, since the coefficients are non-negative, then the Hessian has exactly one positive eigenvalue. Since, for example, when we evaluate it at 1, 1, 1, 1, we get something positive. So it must have some positive eigenvalue. So this means that indeed this polynomial PM for rank 2 is Lorentzian. And this is sort of the only thing we need to prove that it's going to be Lorentzian for any m-complex set, because we can do this by induction. So we do this by induction over well, we actually don't have to do it by induction. We can just, so we just notice that if we take if we take the derivative with respect to Pm, by definition here, we will just get the contraction of M. So it's just going to be the same, the generating polynomial for the contraction. So we have two. We want to check. We have, so by this theorem, what do we call this? By this characterization, which I can't remember the name of it. I think it was M. By this characterization of Lorentzian polynomials that we have now, we need to check this M convexity and this Lorentzian property of the derivatives. But M is for free, since it's defined to be the generating polynomial over the support. And for L, we see that for L, so then we take di1, di d minus 2, Pm, this is just P. This is just the iterated construction. So this is has at most one positive eigenvalue. Since this is of rank 2. And we proved it for rank 2. So it's sort of, we get this for free. So this then characterizes M convex sets and also matroids. So it sort of completes the picture from for stable polynomials. So for stable polynomials, there were some M convex sets and matroids that were not the support of stable polynomials, but for Lorentzian, we get all. So now we'll see how also the Mason's conjecture follows easily from this theorem M. So we have again a matroid on an n-element set. And recall that it is called a subset of E is called independent if it is a subset of some basis. And we denote now by Fk the number of independent sets in K. And then Mason conjectured he had several conjectures of different strength, unimodality and log concavity, and the strongest one was this ultra log concavity. And we'll see how this follows from Lorentzian polynomials. So what we do is we want to associate a Lorentzian polynomial in several variables, and the naive thing to do is just to take the multivariate generating polynomial. So we have one variable for each element in the edge set. So, and then one extra dummy variable to make it homogeneous. And we will now prove that this Im of x is indeed Lorentzian. And how does this give the Mason's conjecture? Well, so recall this, we have this property that if we have a Lorentzian polynomial, if we look at some specific line, or we restrict it to, we restrict it to 2 vectors, then this Alexander-Frankel inequalities implies the ultra log concavity of the coefficients here.
I
Because-
see. Peter, now this is a deliberate choice of the polynomial because you used to divide by factorials,
Mhm.
but you stopped.
Yeah. But we don't want to divide. So it could be natural to divide by n minus I factorial here. Is that what you mean?
Yeah, because earlier in many of your constructions, you were doing like a exponential generating function type.
Yeah. So this would be an easy way. This would be an easier. This would prove. This would not prove ultra log concavity. This would prove like I don't know what it's called, strong log concavity. I think when you divide by k factorials.
Mhm.
But we want to prove the whole thing, so therefore we don't divide here. And this is actually where the sort of Lorentzian approach wins over the Hodge theory approach, because in Hodge theory you cannot do this until now, at least. Well, we don't know how to come up with the Hodge theory approach to prove this. Okay. So I guess we're left with proving this. So again, we need to prove by this characterization. We need to prove this M convexity and this Lorentzian property. And again, this is for free, because it's easy to see that there's support of this, since this is defined sort of, this is a matroid polynomial, and it's easy to see that the support of this is indeed convex. So we're going to prove this. By induction again. Or maybe not by induction. Well, yeah, we do it by induction, sorry. Over the rank. Do we need that? No. Okay, yeah, we can do this. So again, we observe that if we take if E, well, if we have some E in E, then if we take the XE, what did we call it? I am. This is just the contraction. I guess. Of E. Since if we take the derivative of with respect to XE here, anything that don't contain XE will disappear. And if so we sum over all i's that contain E, but then we take away E. And this is the definition of the contraction, right? So this is the contraction. Okay. So by induction now we only have to, well, in checking this, in checking this di1, di n minus 2, and well, d minus 2 im. Has exactly, sorry, one positive eigenvalue. Well, this observation, this reduces it by induction to just consider d x, well, this dummy variable, because the other, for the other variables, we have this, that is equal to the contraction, and then we can, I don't know. There. Okay. So we left to check if the Hessian of this guy has at most one positive eigenvalue. So what do we get? Well, let's compute this. So from the empty set, we will get n factorial t to the, well, t, we don't have t. And then we will get, so sorry. So we will differentiate n minus 2 times with respect to this x naught. So for the, we have exactly one empty independent set, and for that term we will get this if we differentiate n minus 2 times. And for the ones where we have singletons, just we will get we will just get, so we, well, now we can assume it doesn't matter that we have new loops. So just to make, and then we have running out of space. Okay. So we can simplify this. So we divide by I guess n minus 2 factorial. So what do we want to prove? We want to prove that so one of these, so yeah. So we want to prove that so what this so let me think. Yeah, so let me write this down.
You are focusing on a quadratic polynomial now, right?
Yeah, so we want to prove that this is stable or one of these equivalent statements. And one of these, so we have these a number of equivalent statements for a quadratic to be Lorentzian or stable. Well, I guess it's stable. And one of these was that sort of the so one, this is, so by this characterization of stable quadratics, this amounts to proving that the sort of discriminant here, which is then yes, n minus 1 squared, and then that this is greater than 4 times n minus 1 over 2 times this. Oops. And this should hold for all x in R. Okay, so how can we, so this simplifies, so let us, so recall now, okay, so now we recall that we had this, now we have a rank 2 matroid, and this, we have had this parallel classes. So we let now say yi be this sum of overall e in e xi xe. Okay, so what does this say? It says that if we divide by n minus 1, yeah?
yi doesn't depend upon I. Where you
Oh,
must.
sorry, e. It should be e, right? Yeah, sorry. It doesn't make sense at all. P.
Nej. Tack ska du ha.
But now it makes sense, right? So we just sum, so we
Yeah,
make it
based.
into variables, and we sum over all the elements, the variables that in the parallel classes. So these are the parallel classes, P1, P2, and so forth. So what does this say? Well, it says that then, oops. So now we use, so we take the elementary symmetric polynomials in the y. So this is E1 y squared is greater than, so what do we get here? N 2 times n minus 1 over n, right? So correct me if I'm wrong. But and this term now
If you want n over n minus 1.
we do, yeah. Thanks. And we don't want that. Yes, so we get n over n minus 1. And then this term here will be actually, if you think about it, E2 of y. Okay? So say that we have m parallel classes where now m is less than n, right? But we know the Newton's inequalities Say, if you think this is the first Newton inequality says that E1 y squared is greater than 2 times m minus 1 E2 y. And since m is, so we can assume we can of course assume that E2 of y is positive, because otherwise this is true, right? Well, otherwise, if it's negative, then this is obviously true, since this is a square. So, but since there's well, since m is now less than n, we are done. Okay. So it was a little more lengthy derivation than I anticipated, but we got there in the end. So to prove this, we needed to prove this M convexity, which came for free, and then this Lorentzian property. But we observed this, that these polynomials are, so this family of polynomials are closed under differentiation, and this is the crucial property, right? So, and therefore everything reduced to the quadratic case, and this is the, well, the rank 2 case, and this is the rank 2 case. And in the rank 2 case, we may deal with stability. We have all these two tools to see when such polynomials are stable. And in the end, it just boiled down to Newton's inequalities. Well, the first Newton inequality, which is sort of geometric arithmetic mean. Right? Are you with me?
Yeah, so far so good.
So far, so good. So then I thought I'd start with this, the other sort of, so now we want to go to see Lorentzian polynomials. So we want to take well, we don't just want to look at Lorentzian polynomials now, but we want to look at C Lorentzian polynomials on some specific cone. And this cone will be the cone of submodular functions. And this will, in the end, lead to this proof of the Heron-Rotter-Welch conjecture, which I will recall what that is. So again, we have a matrod on E, and then a flat. Recall that this is just a subset of E, so that with this property that if you add anything outside of F, then it increases in rank. So you should think about subspaces. So then this collection of all flats is a geometric lattice. And here we have one example of such a thing with 4 vectors in a plane and then 1 vector orthogonal to the plane. And this leads to this lattice. And for posets in general, we have this Möbius function, and the characteristic polynomials is defined in terms of the Möbius function in this way. And for the graphic matrix, this is essentially the chromatic polynomial. And one can easily see that these are alternating, the coefficients here. Well, it follows from Weisner's theorem, I guess. And these unsigned numbers are called the Whitney numbers, so the second kind. And the seminal results, so first proved it in the case when the matrix is representable over characteristic 0, and then and Katz proved it in the case where you're representable over any field, and then Adebracito and Katz proved it in general using Hodge theory for matrix, that log concavity of these Whitney numbers of the second kind. And what we will try to do next time is to sketch a proof of this. We won't have time to go over all the details, but we sort of give you the, I'll give you the sort of gist of it. To prove this using just Lorentzian polynomials on cones. And for this, we want to define some Lorentzian polynomial, and this is, we define this for each pair of flats. So this is going to be a polynomial, a homogeneous polynomial. Whoops. What happened here? So this is going to be a homogeneous polynomial, but it's no longer going to have just non-negative coefficients. And we'll prove that it's C Lorentzian with respect to some cone C. So this the variables in this are all the flats that sit strictly between K and L. So where does this polynomial live? Well, it then lives sort of, we have this Euclidean space, which I denote by script E here, and then indicating K and L. And these are just the, so we have one variable for each set strictly between K and L. So here, well, this S does not need to be a flat itself. So this is a Euclidean space of dimension 2 to the L minus K minus 2. And we have a specific subspace of this consisting of the modular elements that satisfy this modular law. And here we sort of enforce that even though yk and yl are not defined, when needed, we always set them to be 0. And it's not hard to see that if you're in this, you're a modular element if and only if sort of, if you can find real numbers xi, so that this ys is just the sum of these real numbers in S minus K, where this is 0. Okay, so this is the Euclidean space that it lives in, and we have this subspace of modular elements inside there. And we also have an open convex cone, which will be sort of the cone that the polynomial will be Lorentzian with respect to. And these are the elements in the Euclidean space which satisfies this submodularity strictly. So in order for it to be strict, we can only compare, well, we only require this for incomparable elements S and T. So S should not be a subset of T, or T should not be a subset of S. But I'll have to continue this story next time, but what we will prove later is that we will use sort of, okay, I didn't get that far. We will define this these polynomials inductively. So it's sort of a polynomial defined in the incidence algebra of this, the lattice of flats, since we have for each pair of comparable elements L and K. And we prove that these polynomials have very nice properties, and from them one can sort of use this Bochner method to prove that they are Lorentzian indeed, and then one one have two specific elements in the submodular cone or in the closure of the submodular cone, and if we restrict our polynomial to those vectors, we will actually get the characteristic polynomial or the reduced characteristic polynomial, and this will give the proof of Heron-Rotter-Welch conjecture. But that will happen next time. So I guess I stop here.
Yes, thank you for great talk on that stuff. Any questions?
I had a question. So this obviously a very powerful method for proving strong log concavity, even when you've got a structure of a matroid around. Is there a way to apply it to in other settings where there's not an obvious matroid structure to play with?
Yes, well, it applies to, so Jonathan and I are sort of writing a paper on this right now, and we apply it to different scenarios, and we can sort of, we have, for example, a simple proof of the Alexander-Frenkel inequalities using this. So this method, and there's no obvious matroid there, right. And also there's no obvious matroid for sort of so you can use this to prove that the volume polynomials of associated to projective varieties are Lorentzian, and there's no sort of, there's no obvious matroid structure there, but once you prove Lorentzianness, there is a matroid structure, of course, always.
Right. So it's kind of going the other way. You find the matroid structure from the proof that it's the polynomials are Lorentzian. Okay.
And this is what people have done also when proving that Schubert polynomials and Schur polynomials are, and related polynomials are Lorentzian. Then we get this M convexity and some non-obvious inequalities from that.
Cool. Talk.
Like I said, just one kind of big picture question related to these two proofs. The first one by Hugh and others using Hodge theory. And now you have this very nice kind of combinatorial proof. How would they compare as far as like a length?
Well, our proof is like, I don't know, 8 or 10 pages, and theirs it's 70, I think so.
Oh, okay, that's a good.
And it relies on a lot of algebraic geometry.
Okay.
But they proved more. They proved the Hodge-Riemann relations, higher Hodge-Riemann relations, and maybe so they proved more actually. But for log concavity, but just for the log concavity of in the Heron-Rotter-Welch conjecture, our proof is much shorter. But it should be said that we designed our proof. So this polynomial that we have here is actually going to be the sort of the volume polynomial that they studied too, but we've just taken out the combinatorics of it, and sort of we define it without use of Hodge theory, and see that it has a very nice sort of inductive definition that makes it easy to prove the Lorentzian property.
So, any other questions? All right, well, have a great weekend, and we'll see you on Tuesday.
That's it. Bye.